Okay, so again, in Organic Chemistry 1, we just love these chairs conformations of cyclohexane. So being able to draw them is going to be incredibly important, and being able to draw them correctly, that's the hard part, okay? So let's just start. So we're gonna go through together how to actually draw it, but I just want to point out some really important features first of these chair conformations, okay? So first you're gonna start with the base, the actual chair itself. Important feature of the base, they have 3 parallel sets of lines, right? So parallel, parallel, these guys, and these guys, right? So there are 3 parallel sets of lines in your base, your chair. There are 2 different ways to draw the chair. Remember the flip. So this is sort of what before and after the flip here. Both of them would be correct. If I just said, you know, on an exam, give me the chair conformation of this molecule here, you could start out with either and it's fine. If you have to show the flip, then you need to understand the difference. So let's just look here. Sort of would be how I start drawing them. So I always start drawing them with these 2 lines first. So in my 1 conformation, they're sloping down and to the right. And in the other conformation, those 2 are sloping down and to the left, okay? So depending on which set of parallel lines I started out with, that would be the difference in my conformation, all right? And again, this would represent the flip that occurs. The most important step that everybody messes up on, it's the hardest one, is identifying the axial positions, okay? Which ones are axial up and which ones are axial down. When you look at your chair, so actually I'm going to focus on this guy here before we even look at the bottom. There are 3 carbons that are sitting at a point. This guy, and this guy. And there are 3 carbons that are sitting at a valley, right, in a V. This guy, and this guy. So that's step 1. Is you got to identify which are your peak carbons and which one are your valley carbons. The peak carbons, this is too fat, are the ones that have the axial up position. So you go and draw sticking up above your chair. That's the axial up position. The 3 carbons that are sitting at the valley, at the V, those are the 3 with the axial down position. Okay, so this is the hardest part of drawing your chair conformations. You got to draw the chair base, and then you got to put in those axial positions. So notice incorrect here, I have at the peak, I have one pointed down. This is a peak and something's pointed down. That's not right. If it's at a peak, it's pointed up. If it's at a V, it's pointed down, okay? And then all of these positions have equatorial as well, right? All of these carbons, rather, in the ring have equatorial, and those just sort of stick out of the sides. Notice if the carbon is pointed down, the equatorial should be pointed slightly up, and if the carbon is at the top, should be pointed slightly down, right? This one's at the top, slightly down. This one's at the bottom, a V, slightly up. Okay, I'm not gonna be too much of a stickler about that fact. But yes, there are equatorial positions on all of them. So this is sort of your skeleton of your cyclohexane structure, and we're gonna fill these in, right? If it was just cyclohexane, all of these would just be hydrogens. But what happens, you know, when there's a big old methyl group on there? How does that shake things up, right? So this is the sort of type of questions that we're going to be exploring with these structures, but being able to draw them is essential, okay? So let's go through from scratch here. Okay, so now let's get to actually drawing it. You want to draw parallel lines, slightly sloped down, that are offset from one another. Okay, this is how you start, just drawing these 2 parallel lines, slightly offset from one another, a little bit more. All right, and then on the one side that's down, I'm going to bring it up to a point. So that's that. And on the side that's up, I'm going to go down to a point. So that's that. This one's ugly. Okay. If I wanted to draw the reverse, the flip, I would do the exact same thing, but I would have my parallel lines, these initial ones, going the opposite direction. So now I'm going to have them slightly sloping down, going this direction. Then over here goes up to a point, and over here goes down to a point. Oop, that wasn't enough. It's too much. Good enough. Okay. All right. Okay, so first of all, one of the things that I want to point out, and this is something that's sort of tricky, is everything, right, what we just did here was a flip. So these carbons that are pointed up on this structure, sitting at the peaks, are now going to be pointed down at this structure. Okay, so specifically, if I'm going to go through and label to keep track of my carbons, 1, 2, 3, it's actually, for whatever reason, kind of conventional to start over here. 1, 2, 3, 4, 5, 6. That is 1, 2, 3, 4, 5, 6. Okay, everybody that was sitting at this trough is now sitting at a peak and vice versa. Okay, so keeping track of the carbons when you do this flip is something that's important. Okay. Yeah, we can keep that. I'm actually going to get rid of the numbering. I'll put it back. But let's make sure that we can fill this in with the proper axial positions. Okay, so which carbons have the axial up? Ones that are sitting at the peak, right? So these 3, I'm drawing their axial positions. They're pointed up. And the ones that have axial down are going to be at the valleys. Okay. And then we draw in the equatorial. They just kind of stick out for everybody. Again, if it's pointed up, draw it slightly down, point it down, draw it slightly up. All right, so green are the equatorial, blue are the axial in this particular one. And actually, I'll go ahead and do some distinction between these because we'll see why in a second. Okay, now I'm going to go through and put those numbering in again. Okay. One of the things that you want to notice is that axial positions and equatorial positions are going to have changed here. What was axial on one side is now going to become equatorial once the flip occurs and vice versa. So if we look here, again, if we're going to identify which atoms have the axial up position, those are going to be the ones that are sitting at that peak. Well, that's 2, 4, and 6, which were previously sitting at the valley. So it's the equatorial bond from the 1 that's now going to become this axial up here, right? So this bond here is now my new axial up. Same with 2. This one here is now going to be axial up. And 4, what was my equatorial, is now axial up. And what was used to be in the axial down position is now going to be in that equatorial position. Okay, likewise, if we go and identify all the axial down positions, that's going to be at the troughs. But 1, 3, and 5, they used to be at peaks. So what's actually going to be pointed down, so if we look at carbon 5, it's going to be this bond here. It's what's going to be pointed down now. Same with 3, what used to be the equatorial position is now going to be the axial down. And same thing with 1. Put my label in a bad place. What used to be equatorial is now axial down. Okay, and then that means that all of my formerly axial up are now going to be these equatorial positions. Okay, so this is what happens in the flip, is you have something that was in an axial position going to an equatorial position, something that was in an equatorial position going to an axial position. Being able to draw it is extremely tricky, so I would recommend going through this video a few times and just sort of getting the whole process down. Okay. There's no difference in energy between those two structures when there's only hydrogens on your when you only have cyclohexane all by itself, right? All of those bonds are hydrogen. So they will flip through. Any one would be as equally stable at any moment, right? Either of those two conformations. However, you start to get some interesting stuff that occurs once you put something else on there. So a methyl cyclohexane, for example. When this chair flip occurs, so again, let's just convince ourselves that there is indeed a chair flip happening. Notice in this structure, we have these parallel down lines, and in this one, they're parallel up, right? So these are these two different conformations. This carbon that used to have that axial up position, it was located at a peak, and then this flip occurred, and now it's located at a trough. And what does that mean in terms of that substituent right there? That means that it used to be in the axial up position, the flip occurred, and now it's in the equatorial position. Okay, another thing that you can do, another way to represent this is with those Newman structures again. This is a great way to show this. We saw with the Newman projections before of these molecules, right? You have these 1, 2, up. There's another axial up on this particular carbon that's not explicitly drawn in your Newman projection. You have your axial down positions. There's also one located here that's not explicitly drawn. And then you have your various equatorial positions. Right, remember that from our Newman structure. It got a little busy. I just want to make sure that we can identify all those sites. Okay, I'm going to get rid of this labeling now so that we can see what's going on. But yeah, just to be clear, right, we can sort of look at our Newman projection and also see that in this case, the substituent is now in the equatorial position. When we do our Newman projection, or when we do our chair flip in the Newman projection, it's sort of equivalent to rotating these back carbons inward and these front carbons around. And again, most importantly, we're going to see that everything that was axial becomes equatorial, and everything that was equatorial becomes axial. Okay, so now this is just this sort of showing that chair flip instead of being in that chair conformation that we spent a lot of time drawing. This is showing the same thing in these Newman projections. So where are we going with this? Is the idea that not all sort of conformations are the same. So if we take methyl cyclohexane, for example, we have two possibilities. It can be in the staggered position. It can be in the axial position. Right, so that would be this guy. Or it could be in the equatorial position. So which one would be more stable? Well, maybe actually if we sort of go back to our Newman projections here and imagine that instead of just having this X, we have a methyl group. Can you sort of tell which one it would be more stable? Which one seems to have less sort of stress going on? You can hopefully see that your axial position here is going to have more sort of strain because of that methyl position in the axial position, whereas over here, the equatorial position, that methyl group just has a lot more room, right? So it turns out that when we look at this sort of distribution, this equilibrium that goes on, again, this here is just representing the flip that occurs. It actually lies quite heavily in favor of that equatorial position. Only 5%, if you could freeze time and go in there and count them, only 5% of the time would you find that methyl group in the axial position, meaning that it is a higher energy structure. Remember that we had those gauche interactions, right? Those were these methyl groups that, despite being staggered, remember cyclohexane can adopt that perfect torsional angle sort of situation. Nonetheless, there's this gauche interaction that, although staggered, you still have these big groups that are too close to one another. This is basically what you have when you have cyclohexane, where the methyl group is in the axial. So this is the axial position. It's equivalent. It's sort of equivalent in our rotational conformational analysis to that gauche interaction. Whereas when you're in the equatorial position, it's equivalent to being in that anti-conformation, that lowest energy conformation. And the effects only get more dramatic the bigger the group you have, right? So again, this equilibrium is representing the flip, where here it's the axial, and over here we have the equatorial. And here we have this variable substituent here. And what this table is showing us is what happens when I put in a chlorine. Well, at equilibrium, you're going to get a 70-30 distribution to equatorial to axial. So over here is 70, over here is 30. When you make it an OH group, all of a sudden you get, 83 to 17. We saw our methyl group was 95 to 5. Ethyl group, the bigger that is, the bigger it's going to be. And then notice here, this is if we had a tert-but group. And let's just put in what that would look like real quick so we can visualize maybe why that's such a dramatic distribution of equatorial to axial. Right, remember, what does that tert-but group look like? It's got a carbon that's bound to 3 other methyl groups. So you see, this is just a hugely bulky group here, which is why it lies so heavily in favor of the equatorial position. Okay, so now we're ready to move on to stereoisomers, but let's make sure that we can all draw our chairs and use them to sort of tell whether or not which conformation is going to be more stable.